So we're moving into the part of Calc 3 where it gets, I think it gets a little bit more challenging because you're going to be asked to do things that you're not used to. And probably throughout your whole life of math, you've been asked to show your work. And a lot of you guys that are really good at math always kind of complain like, what do I don't have any work to show. I just did it in my head. But in this case, what we're doing is proving something to be true, which means the work is the answer to the question. You have to show a step-by-step or logical reasons for why you believe something's true. And we've talked about that a little bit in earlier videos. The Nth Term Test is a pretty basic one. We also talked about the known series that were, and so you need to be careful when you write them up. You have to use exact and precise language. One thing that's really big that people have trouble with is the difference between this and this. And in an earlier video I talked about this, but I just want to re-emphasize this. This is talking about a series. This is talking about a sequence. In fact, this is talking about a series where I'm adding up the terms of this sequence. So every series, if you watch the very first video of last week, every series has two sequences associated with it. You have this sequence here. That's the sequence you're adding up. But then you also have the sequence of partial sums, which is often referred to as this, where this represents, so in this case, S sub 1 would be equal to A sub 1. S sub 2 would be equal to A sub 1 plus A sub 2. S sub 3 would be equal to A sub 1 plus A sub 2 plus A sub 3, etc. So there's the series, there's the sequence that the series is adding up, and then there's a sequence of partial sums. All of these are intertwined or interconnected. And whenever you're talking about them in the proofs, you need to be clear what it is you're talking about. For example, in the Nth Term Test, if you remember, it says if the limit as n approaches infinity of a sub n, if it is not 0, not a to the n, a sub n, if it is not 0, then we can conclude that the series is divergent. And so you can see the difference here, that in this case I'm talking about the sequence, in this case I'm talking about the series. So I looked at the sequence that's being added up in this series, found out something about it, and because of this test, it told me that something about the series. This is not, it's not true that whatever happens with the sequence also happens with the series. This is just a proof that people smarter than us have figured out, that they say if you can show that the sequence doesn't equal 0, doesn't approach 0 as n approaches infinity, then you know for sure that the series diverges. And as I emphasized in the earlier video, it doesn't say anything about if it approaches 0. It doesn't tell me anything. Okay, so so again, just trying to reemphasize, you got to be precise in your language when you're proving these things. So we're going to look at a couple different convergence tests. First one is the direct comparison test. So if you have if you haven't printed off your help sheet, you should go print it off now so you can have it beside you. You really want to be able to look at that so you can, because you're going to be using that on all of the any test or quiz you use. You can use that resource sheet. So you want to get used to using it. So find the direct comparison test on there, and the way the direct comparison test says, it says that you assume there exists an m greater than 0 such that 0 is less than or equal to a sub n, which is less than or equal to b sub n, for all n greater than or equal to m. Okay, now that's some fancy language, but you got to get used to this because this is proofing language, or language of proofs. So basically what we're saying is there's some number, some term number you can go out in the sequence, and you're going to be able to find a, like say at the fifth term, from the fifth term on, that's what this is saying, from the fifth term on, this sequence is going to be smaller than that sequence. Or maybe I have to go out to the 1000th term. That would be, then my n would be 1000. And I would say from the 1000th term on, this sequence is smaller than that sequence. So basically what we're trying to show is that the terms of this sequence is smaller than that sequence, but also that all of them are bigger than 0, so they're all positive. This only works for positive sequences in series. Okay? So that's what this language means, is we're trying to find one sequence that's small, that all the terms after a certain point are smaller than this other sequence. Okay, and if we can do that, then if this series converges, then this other series converges. So the idea is if we can take the sequence from this series and the sequence from that series and show that the terms of this sequence are, after a certain point, always bigger than the terms of that sequence, and this bigger sequence, its series converges, that would force this smaller sequence, its series, to converge. So notice in this, you got to be very careful that sometimes we're talking about a sequence, sometimes we're talking about the series. We're looking at the sequence again to show something about the series. So when you're writing up your proof, you got to be very clear on that. Now there's a second part to this proof. It also says that if a sub n, that's the smaller one, diverges, then the series associated with b sub n, that's the bigger sequence, would also diverge. So in this case, you either know something about this guy. If you know something about this guy, if you know that he converges, that would mean the guy smaller than has to converge. Or in this case, if I knew something about the smaller guy, if I knew that the smaller guy diverges, that would force the bigger guy to diverge. Okay, now, what this doesn't say is what if I know that a sub n, converges? Well, notice that doesn't tell me anything. This test doesn't help me. Okay, I don't want to know that the series associated with the smaller one is convergent. I want to either know that the series associated with the smaller sequence is diverging, and that would force the bigger one to diverge, or I want to know that the series associated with the bigger sequence converges, and that would force the smaller series to converge. Okay, so that's the idea. So the key to this direct comparison test is you got to set this up. You have to establish this. So generally what you're doing is picking the sequence that goes with your given series, and you're making up another one, a different one. Okay? And so let me show you an example of that. Let's see if I've got one over here. Okay, so here's an example. I want to try to prove either convergence or divergence of this series. So I noticed that it looks almost like a p-series because you got this into the number on the bottom, but you got this extra plus into there. So it's not a p-series. You know, if this was just n runs from 1 to infinity of n squared over n to the fifth, that would be the same thing as n running from 1 to infinity of 1 over n to the third, right? And that would be a p-series, and we could show that that converges. No problem. But you can't do that with this guy because you have that extra little plus n on the bottom. So I suspect that it does converge because it looks kind of like the p-series, and that's really what the comparison tests do. Is you pick a series that looks kind of like a known series, and then you make a comparison. So remember, in the comparison test, I need to establish this thing here. So as a part of my proof, the first thing I need to do is establish my a sub n. So I'm going to say my a sub n is the sequence associated with the given series. So a sub n is n squared over n to the fifth plus n. So I have to state that in my proof. Then I'm going to state my b sub n, because that's also important. And I'm going to pick something that I can prove is bigger than the a sub n, and also something that I know about the series associated with it. So I'm going to say b sub n is equal to n squared over n to the fifth, which we all know is 1 over n to the third, right? Now I know something about the series associated with that. That's a p-series. This is a sequence. It's not a series, but the series associated with this sequence would be a p-series, right? So I know how that one behaves. In fact, I know that it converges, which is what I want, right? I want the b sub n to converge. So that means I'm going to have to show that b sub n is bigger than a sub n, right? So I'm going to make that statement. A sub n is less than or equal to b sub n. Now I have to show that. How do I know that a sub n is less than or equal to b sub n? Well, I'm going to say for all n, right? Because up here it said I just got to pick some number out there, but it's actually for any n. So the n would be from 1 on, right? So wait, I think that's true. If I put a 1 in there, that'd be 1 half. And this would be 1 over 1. Yeah. Okay. And how do I know that? Because I know that n to the fifth plus n is always bigger than n to the fifth. Isn't that true? If I take n, because remember n runs from 1 to infinity, so it's always going to be a positive number. So this right here is clearly always going to be bigger than that, because this is just n to the fifth plus 1 more. So I've established that a sub n is going to be less than or equal to b sub n for all n, because this is always going to be bigger than that. Okay, so I've made that very important initial statement. So now, because a sub n is smaller than b sub n, that means I can use the convergence test, because I know that the series associated with b sub n converges. So I'm going to do that. That's my next step, is I have to say, okay, now that I got the relationship I want with a sub n and b sub n, I'm going to say b sub n running from 1 to infinity. And notice I don't need to write it out because I've already set it up here. B sub n converges. How do I know it converges? Because it's a p-series with p equal to 3. All right? So that anyone that knows anything about the known series, right? If we have a p-series with p equal to 3, which is greater than 1, right? We know that it converges. Okay, so now we've established that every term of the b sub n sequence is bigger than every term in the a sub n sequence, and we just showed that the series associated with b sub n converges, so therefore we can conclude, whoops, stop that. Therefore, this series. Now, since this is my final statement, I'm just going to go ahead and write it all in again, even though I could put a sub n there, but just because I want to make my final statement with some pizzazz, right? Plus, man, this thing's freaking out of line. Okay, so therefore, this series also converges, because that's exactly what this tells me, right? If I have my b sub n converging, then my a sub n also has to converge. Right? So there's my proof. So I've just shown in a series of language or notation and facts that I've shown that this series is convergent. Okay? Now, let's try another one. Let's look at this guy. N squared minus n over into the fifth plus n. Okay? So I want to show either convergence or divergence of that series. And so if I just go down the same road I was going before, let's just jump on this and say, oh, a sub n, it worked good last time. A sub n is equal to n squared minus n over into the fifth plus n. And then this still kind of looks like into the squared over into the fifth. So I'm going to choose b sub n to be equal to n squared over into the fifth, which is really just 1 over n cubed, right? So now I have to establish that a sub n is less than b sub n for a certain n. Now, is that possible? Well, I think it's still possible, isn't it? Because it's still, the top in this case is always going to be smaller than that top, right? And the bottom is always going to be bigger. So I'm going to say, yeah, this still works. So I could say because n squared minus n is always bigger than n squared, and n to the fifth plus n is, is always bigger. It's always smaller. And n to the fifth plus n is always bigger than n to the fifth. So if I have a fraction that's smaller on top and bigger on the bottom, that makes the overall fraction smaller than that fraction. Okay? So it took a little bit more evidence to show that a sub n is less than b sub n, but it still worked. So then I'm going to go ahead and say what I said before. Well, that I also know that the series n running from 1 to infinity of b sub n, so the series associated with that sequence, converges. How do I know it converges? Same reason I said before, it's a p series. P series with p equal to 3, which is greater than 1. And then I can conclude once again, therefore, the infinite series running from 1 to infinity of n squared minus n over n to the fifth plus n also converges. Right? Okay, let's try one more example. Let's say that we have summation from 1 to infinity of n squared plus n over n to the fifth plus n. Maybe we'll just do it like that. N to the fifth. Okay? And I want to show that that's convergent or divergent, one or the other, right? So again, it looks kind of like the one we did before, so we just jump on and say, okay, let's let a sub n equal n squared plus n over n to the fifth. And let's choose our same b sub n. It seemed to work last time. A sub n, or b sub n is equal to n squared over n to the fifth, which we all know is 1 over n to the third. Now when we go to show that a sub n is less than or equal to b sub n for all n, or maybe for some certain n, now this becomes a lot more troublesome, because notice the bottom is the same and the top is actually bigger than that. And that's a bummer. So I'm not going to be able to actually establish this. In fact, I could actually say with confidence that my b sub n is always smaller than a sub n, because the bottoms are the same and the top of a sub n is bigger than the top of b sub n. And that doesn't work because we know that the series associated with b sub n converges. And I don't want the smaller one converging, because that doesn't tell me anything about the bigger one. Now, if this was a divergent series, then that would work. But because this is smaller, this doesn't work. So this direct comparison test is not going to help us here. Fortunately, we have this little thing called the limit comparison test. If you look on your sheet, find it. Now the limit comparison test is nice because it doesn't require anything about any association between the a sub n and b sub n. You still choose the a sub n and b sub n. In fact, it does say that let a sub n and b sub n be positive sequences. So that's the only requirement. Okay? And then what you do is you take the limit. You take the limit as n approaches infinity of a sub n over b sub n. Okay? So notice we don't have to show that a sub n is bigger than b sub n or b sub n is bigger than a sub n. It doesn't matter what, we don't care about that. All we're going to do is pick an a sub n and b sub n that are both positive sequences, and then we're going to take the limit. And depending on what we get for the limit, it's going to tell us different things. If L is greater than 0, then a sub n, the series associated with a sub n, converges if and only if b sub n converges. Which means, now this if and only if means it goes both ways. That means that if this guy converges, then that guy converges. If this guy doesn't converge, then that guy doesn't converge. So basically they behave the same. That's what this is saying, that this guy behaves the same way as that guy. So if I know anything about this guy or that guy, then I can say the same thing about the other one. Okay? That's if I get an L that's greater than 0. I guess I should say greater than 0, but let's do it this way. L greater than 0, but less than infinity. Okay? Because the second part of this test is if L equals infinity, then something else. If L is equal to infinity and a sub n, notice that's the top sequence, the series associated with the top sequence converges. So if L equals infinity and a sub n converges, then we can conclude that that lower one converges. Right? And then finally, the third condition is if L is equal to 0 and the lower guy converges, then the series associated with the upper guy converges. Okay? So basically in the limit comparison test, we're usually hoping for this first one because it's the biggest statement. If I can get L to be some number between 0 and infinity, then whatever, as long as I know one of them, I can say something about the other one. Okay? So let's use that new knowledge to go back and take a look at this guy. So we can't establish that, so we're going to forget about that. I mean, we can't establish something we don't want. So what we're going to do, instead of establishing a sub n being smaller than b sub n or anything like that, we're just going to take the limit as n approaches infinity of a sub n over b sub n. Okay? And of course that would be equal to the limit as n approaches infinity of a sub n would be n squared plus n. Whoops. Whoa, that was weird. Okay, I'll just erase that. Okay, as n approaches infinity of n squared plus n over n to the fifth divided by b sub n, so that'd be like multiplying by the reciprocal, right? So then I end up with limit as n approaches infinity of, well, this would be n to the fifth plus n to the fourth over n to the fifth. Now I'm letting n approach infinity, and when n approaches infinity, these become the dominating feature, and so this is in a ratio of 1 to 1, so this limit equals 1. And we rejoice. Yay, because we got what we wanted. We got an L that's bigger than 0, but less than infinity. So that means that the two series behave similar. So I'm going to erase this to make some room here. We're using the limit comparison test, right? So because we got this L equals 1, so L, well, that's my L, right? So L is greater than 0. Therefore, and also I know that the series of B sub n, as n approaches from 1 to infinity, is convergent. How do I know it's convergent? Because it's a P series. With P equal to 3, which is greater than 1. So we have L greater than 0. We have this series converging. Therefore, we can conclude that the other series also converges. Because we met this condition, and we found out that one of them converges. So remember that first line says if one of them converges, then the other one converges. If one of them diverges, then the other one diverges. They basically, this if and only if means they behave the same as each other. Okay, I think that'll get you started on this idea of proof. So notice that I'm very exact in my language. When I say limit, I keep writing the limit until I've taken the limit. I'm very careful about when I say a sub n and when I say the summation of a sub n. This is a sequence, that's a series. Here I'm calling it a series. I'm saying it's converging, right? So be very careful with your language and with your notation, and start trying your hand at this.